Okay, the masked professor once again picks up his cudgel. See, mask. Sorry, I screwed up the last take, so I had to start over again. Today we're going to be talking about tolerance and prediction intervals. Although why they didn't say prediction and tolerance intervals, since prediction intervals are first, I'll never know. This is a bonus class, and we're going to have two bonus homeworks, 11 and 12, that will be able to be taken. Actually, I guess they would be 12 and 13. You can go on Wiley Plus and do those homeworks, and they can replace lower grades in your first 10 homeworks. All right, so a normal 100 times the quantity 1 minus alpha percent prediction interval, or PI, on a single future observation from a normal distribution is given by x bar minus t alpha divided by 2 with n minus 1 degrees of freedom times sample standard deviation times the square root quantity of 1 plus 1 divided by n is less than or equal to x of n plus 1, our next observation, less than or equal to x bar plus t alpha divided by 2 with n minus 1 degrees of freedom times sample standard deviation times square root quantity of 1 plus 1 divided by n. Our prediction interval for x of n plus 1 will always be longer than the confidence interval for mu, our population mean. So there, take that. All right, so here they're going to give us an example 811, alloy adhesion. So the load and failure for n equals 22 specimens was observed, and it was found that x bar equals 13.71. And sample standard deviation equals 3.55. The 95% confidence interval on mu was 12.14, less than or equal to our population mean, less than or equal to 15.28. Plan to test a 23rd specimen. So we're going to predict what interval that is going to fall into. All right, so x bar minus t alpha divided by 2 with n minus 1 degrees of freedom times sample standard deviation times the square root quantity of 1 plus 1 divided by n is less than or equal to x of x n plus 1 less than or equal to x bar plus t alpha divided by 2 with n minus 1 degrees of freedom times sample standard deviation times the square root quantity of 1 plus 1 divided by n. All right, so for our t alpha divided by 2 with n minus 1, alpha divided by 2 is going to be 0.025, n minus 1 is going to be 21. And that is 2.080. I'm assuming you've been watching my videos and know how to find that number. So 13.71 minus 2.080 times 3.55 times the square root quantity of 1 plus 1 divided by 22 is less than or equal to x 23 less than or equal to 13.71 plus 2.080 times 3.55 times the square root quantity of 1 plus 1 divided by 22. And that means that our next specimen will be between 6.16 less than or equal to x23 less than or equal to 21.26. Wow, that is a huge prediction interval compared to our confidence level, which you can see up there. Okay, so our interpretation, a prediction interval is longer than the confidence interval. The confidence interval is the estimation of the parameter mu, but our prediction interval is an estimate of a single future observation. So we give ourselves a lot of wiggle room on that basis. Yep. All right. So now let's do a couple of prediction interval problems, and then we'll get into tolerance intervals. All right, so I have chosen a couple of problems in the old 5th edition book that has served us so faithfully over the years, so faithfully. And we are going to do problem 8-61 from the 5th edition book, of which your book is the 7th edition. 8-61. Consider the tire testing data described in exercise 827. Compute a 95% prediction interval on the life of the next tire of this type tested under conditions that are similar to those employed in the original test. Compare the length of the prediction interval with the length of the 95% confidence interval of the on the population mean. Okay, so we are given that our x bar for that problem, and you may remember we did this problem before, that x bar equals 60,137.7 kilometers, that our sample standard deviation is 3,645.94 kilometers, and that, sorry about that, and that our n is equal to 16. Okay, so we want the prediction interval for n plus 1. All right, well, we look at our formula, x bar minus T alpha divided by 2 times sample standard deviation times the square root of quantity of 1 plus 1 divided by n, less than or equal to x of n plus 1, which is going to be equal to 17, less than or equal to x bar plus t alpha divided by 2 with n minus 1 degrees of freedom times sample standard deviation times the square root quantity of 1 plus 1 divided by n. Okay, well, we have all our numbers except T alpha with n minus 1 degrees of freedom. So, what a surprise that I brought along my table. If you're going to do a lot of work in statistics, I suggest that in the Appendix A, you put those little glue-on reinforcement things around the holes. This table's hardly been used and already the holes are wearing. All right, so for a 5% alpha, that's going to be a 0.025 that's going to be a 0.025 alpha divided by 2. All right, so I sequester my alpha divided by 2 column. Then I come over here. We have a sample size of 16, so n minus 1 means that we have 15 degrees of freedom. And therefore, our T alpha divided by 2 with n minus 1 degrees of freedom is 2.131. All right. And I will put that up here, T alpha divided by 2, n minus 1 degrees of freedom, 2.131. All right, now we have, oh, sorry, have to widen that out again. All right, that's too wide though. And that's just right. All right, so now we have to substitute in our numbers, and this is going to run over to another line, I'm afraid. So x bar equals 60,137.7, excuse me, it should be 139.7 minus 2.131 times our sample standard deviation, which is 3,645.94, right? And then our square root quantity of 1 plus 1 divided by n, or n is 16. Oh man, that's sloppy. Oh well. Less than or equal to x 17, which is less than or equal to 60,139.7 kilometers plus 2.131 times 3,645.94 kilometers, times the square root quantity of 1 plus 1 divided by 16. Okay, well, luckily, I've got my Excel sheet ready to go here. All right, so Excel sheet ready to go. Start putting in my numbers. 60,139.7 minus 2.131 times 3,645.94 times the square root quantity of 1 plus 1 divided by 16. Yeah, that works. All right, so our lower bound on our prediction interval is 52,131.08. All right, so 52,131.08 kilometers. It's going to be less than or equal to x 17 less than or equal to, oh wait, I have to calculate that still. What a mistake on my part. $68,148.32 kilometers. All right, so 68,148.32 kilometers. Okay, well, and that is, of course, our prediction interval. All right, so in a few minutes, we're actually going to figure the tolerance interval on this same problem. All right, let's do one more problem here, and then we'll talk about tolerance intervals. All right, so problem 8-63. This time I'll write prediction interval across the top. Sometimes I wish I had editing and everything so that when I make a little mistake, I could just keep going and redo that part. But oh well, that's life in the big city. All right. Problem 863. Consider the syrup dispensing measurements described in exercise 829. Compute a 95% prediction interval on the syrup volume in the next beverage dispensed. Compare the length of the prediction interval with the length of the 95% confidence interval on the population mean. Well, you know what? We're not going to worry about that too much. All right, so we are given from problem 829 that our sample size is 25, that our X bar equals 1.10 fluid ounces, and that our sample standard deviation equals 0.015 fluid ounces. All right. Once again, our formula is X bar minus T alpha divided by 2 with n minus 1 degrees of freedom times our sample standard deviation times 1 plus the square root quantity of 1 plus 1 divided by n less than or equal to x of n plus 1 less than or equal to x bar plus T alpha divided by 2 with n minus 1 degrees of freedom times sample standard deviation times the square root quantity of 1 plus 1 divided by n. All right, well, what do we not have? We do not have our T alpha with n minus 1 degrees of freedom. Okay, so once again, because it's 95%, it's going to be in the 0.25. Okay, so I'm going to make this larger. And I'm going to move it up the tiniest bit. All right, then I take my pieces of paper. We know that alpha divided by 2 for a 95% interval is 0.025. So I put my paper next to that. Now, our sample size is 25. So I've got to go down here. There's 25. N minus 1 becomes 24. So our T alpha divided by 2 with n minus 1 degrees of freedom, in other words, T of 0.025 with 24 degrees of freedom is 2.064. Quick, let's write that down. Okay. Oh, it's because I went down. All right. Tighten this up a little bit. All right. So, T of 0.025, our alpha divided by 2, and 24 degrees of freedom is 2.064. Now we have all our numbers. We're going to substitute them into our equation up here. All right, so we know that X bar is 1.10 fluid ounces minus T of 0.025 with 24 degrees of freedom, 2.064 times our sample standard deviation, 0.015, and again that's denominated in fluid ounces, times the square root quantity 1 plus 1 divided by 25. All right, so that is less than or equal to x26 is less than or equal to 1.10 fluid ounces plus 2.064 RT alpha divided by 2 with 24 degrees of freedom times 0.015 fluid ounces times the square root quantity of 1 plus 1 divided by 25. Okay, so what is our interval for x26? I don't know about y'all, but the excitement is getting to me. All right, so equals 1.10 minus 2.064 times 0.015 times the square root quantity of 1 plus 1 divided by 25, right parenthesis, and Bob's your uncle. All right, so I am going to call that 1.07 fluid ounces, and then what is our upper I know the excitement is getting to me. I'm sure at home you're riveted. I'm going to call that 1.13. All right, so as you can see, oh, and I should have put fluid ounces. Don't assume the units. All right, so 1.07 fluid ounces less than or equal to x26, our next sample, less than or equal to 1.13 fluid ounces. All right, so that's a pretty tight, prediction interval. And I'm curious to see what the confidence interval is. Now, ordinarily, I'd have to go through and look up everything and recalculate the confidence interval. But in this case, I have the ability to just look in the back of the book and say the confidence interval is 1.094 fluid ounces. And the upper bound on that is 1.106 fluid ounces. Oh, wait. Yes. Square bracket. It comes back to me. All right, so that's the 95% confidence interval, whereas this is the 95% prediction interval. All right, so you can see, even though our prediction interval is pretty tight, still a bit larger than our confidence interval. Okay, meanwhile, back at the slideshow, and let's jump into this quickly. All right, so a tolerance interval means what amount of variation are we going to allow, usually in an industrial process. So our tolerance interval for capturing at least gamma percent of the values in a normal distribution with a confidence level alpha times the quantity 1 minus alpha minus 100 times the quantity 1 minus alpha percent is x bar minus k times our sample standard deviation at the lower tolerance interval, and x bar plus k times the sample standard deviation. Well, you may be saying to yourself, k, where did k come into this? Where k is a tolerance interval factor found in appendix table number 12. Values are given for gamma equals 90%, 95%, and 99%. And under each of those, for 90%, 95%, and 99% confidence. All right, I'm going to show you the table and how that works in a minute. But first we'll look at an exciting example. 8-12. Oh man, I am so tired. I've been making videos like a madman. The load at failure for n equals 22 specimens was observed. It was found that x bar equals 13.71 and sample standard deviation equals 3.55. Find the tolerance interval for the load at failure that includes 90% of the values in the population with 95% confidence. So from our appendix table 12, our tolerance factor K for n equals 22 with gamma equals 90% and 95% confidence is K equals 2.264. So our desired confidence interval, x bar minus K times sample standard deviation, and x bar plus K times our sample standard deviation. All right, so we put in our numbers and we say the tolerance interval is between 5.67 and 21.74. So we can be 95% confident that 90% of the values of the load at failure for this alloy are between those two numbers. Okay. What y'all don't know is it's extremely close to lunch, and I'm starting to get weak from lack of chemical energy. Okay, so, right, important concepts, terms. All right, now we switch to the camera. Now, boom. Now, we are going to calculate the tolerance interval Well, I tell you what, first let's look at what the table looks like. Okay, so you have two tables. There's table 12, which is for two-sided intervals. Okay, so you have your confidence level and your probability of coverage, right? So let's focus in So this is a 90% confidence level. And then down below, we have our probability of coverage, right? So in our problem that we saw before, they wanted 90% coverage. So they wanted to cover 90% of coverage with 95% confidence. All right, so we have to go down a wee little bit more. All right, and how many samples were in that problem? I've already forgotten. Luckily, n equals 22. All right, so what we're going to do is we're going to come down here, and I'm going to tilt so that we can see 22 with 90% coverage and a confidence level of 0.95 or 95%. All right, so I've got to tilt down further, but I'm going to use my usual trick of putting a piece of paper, and then I come down here and you can see there's 22, and there is 2.264, which matches up with 22, there you go. My paper won't stay. With which matches up with the number that they had quoted in the example problem. All right, so these tables introduce a new kind of complication in reading the tables, right? It's not the alpha versus nu tables that we have in with a t-table or a chi-squared table. It's that you have to be considering which of the two levels goes where. But I digress. All right, so let's widen this out so we can see the edges of the paper, because I have a bad tendency to write right up to the edge. Oh, okay. All right, so now let's look at the same syrup dispensing problem, but calculating the tolerance level or the tolerance interval. Okay, and to make it more interesting, we want to cover 95% of samples at a 99% confidence level. Okay, and we will do this as a well, let's do it as both a two-sided and one-sided. All right, so two-sided tolerance interval. All right, so for a two-sided, we get out our faithful paper. Now, in your book, there are two tables, table 12 and table 12. What the hell? Okay, so they're both table 12, but this one, which is page A30, cross out where it says 2 and put 1. And you will be able to tell it because the first number right here is 10.253, whereas on the two-sided it is 15. I actually had to quickly check in my other book, which is labeled correctly for these tables. All right, but we are looking right now at the two-sided table. All right, so we want a probability of coverage at 95% and a 99% confidence level. All right, so that means that we are all the way over here, our 99% confidence level, and we want 95% coverage. All right, so as usual, I get my two pieces of paper, all right, and I put it down so that I can see, and because the sample size is 25, I put it down here, and let me make this larger, right, and you can see that my K in this situation is 2.972. 2.972. K equals 2.972. Right, that is what K equals, right? 25. Yes, okay. All right, so we widen out so we can see both sides of the paper. Now, it's super simple because our tolerance interval is going to be X bar minus K times sample standard deviation and X bar plus K times sample standard deviation. So that means that X bar is equal to 1.1 0 minus 2.972 times our sample standard deviation, 0.015, and then our upper bound is going to be 1.10 fluid ounces for our X bar plus 2.972 times sample standard deviation of 0.015. Oh man, it's pretty large when you write it out that way. All right, so, need to get on my Excel sheet again. All right, so Excel, here we go, equals 1.10 minus 2.972 times 0.015. Okay, so my lower side of the tolerance interval is 1.06. And my upper side, calculate that real fast, 1.10 plus 2.972 plus times 0.015. And we enter that, we get 1.14458, so I'm going to put it down as 1.14. All right, so again, that's two-sided. But what if we want a one-sided tolerance interval using the same thing? Okay, well, because we don't want to give any more syrup than we have to our customers, we are going to work the upper side. So that's going to be X bar plus K times our sample standard deviation. And that is, well, first of all, we have to find our K. Now this time I have to use my one-sided interval sheet. I'm going to work on the assumption we're working to the same standard, so my 99% confidence level and 95% coverage. I'm going to look here at the 25 row, and I've got 2.633. I don't know if y'all can see that. You're gonna have to trust me, no matter how little you trust me now. And 2.633. All right, so 1.10 plus 2.633 times 0.015. All right, so therefore, it's going to be 1.139. $1.139. Now I put down 1.139 because I wanted to differentiate, oh, bloody hell. I wanted to differentiate from here where our upper tolerance interval is 1.14, right? Really, to stay consistent, I should have rounded to 2 decimal places, which would have been 1.14. But just to show them, I cannot believe that my Sharpie is running out of ink, since the only thing I've been marking up is papers for you guys to look at during these lectures. All right. So here is our prediction interval problem for our tire test. Now let's do the tolerance intervals. All right, now tires, well, first of all, let's just do two-sided. All right, and let's do it with 90% coverage and 95% confidence level. All right, so that implies that K is equal to what? All right, I've got my two-sided table here. I want 95% confidence and 90% coverage. And what is my my sample size is 16. Okay, so I'll move this a little. All right, again, I'm using my two-sided table, 95% confidence level, 90% coverage. I blow it up a little bit. Uh-oh. Our sample size is 16, so my K equals 3.514. 3.514. .514. Of course, my tolerance interval is X bar, our sample mean, minus K times sample standard deviation, and the other side is X bar, the sample mean, plus K times the sample standard deviation. All right, so that is going to be, oh, well, bloody hell. All right, so our lower end is going to be 60,139.7 minus 3.514 times 3,645 94. My upper end is going to be 60,139.7 139.7 plus 3.514 times 3,645.94. Oh, barely got it in. All right. So, once again, all I'm going to do is come over, use Excel, equals 60,139.7 minus 3.514 times 3,645.94. And then I'll do the upper calculation. All right, so our tolerance interval with this set of tires that we have been testing to include 90% coverage at a 95% confidence level is 47,327.87. Oh man, I didn't memorize the number while I was saying it. All right, 47,327.87. The upper end of our tolerance interval is 72,000 951.53. All right, so suppose we want to do one-sided, again with 90% coverage, and 95% confidence. Now, should we do the upper or lower end? We probably want to do the lower end. We want our tires to last a certain amount of time, or our customers will complain too much. Damn those customers and their complaints. All right, so this time I'm not using the two-sided, I'm using my one-sided intervals. My confidence level at 95% and my coverage at 90%. All right, and let's blow this up as much as I'm afraid of running out. And then I put this under the row 16. So my tolerance, or my K, to calculate my tolerance interval becomes 2.033. .033. All right, so not tighten, but expand. There we go. K equals 2.033. All right, so since I'm calculating a lower end confidence bound, it's X minus K times sample standard deviation. All right, so that equals 60,139.7 minus 2.033 times 3,645.94. Okay, well, so what then is that lower tolerance? Oh, wait. Here we go. I can just... use this calculation, 2.033. Is that right? Yes. All right. So then our lower tolerance interval, our one-sided, we expect tires to last at least 52,727.5 kilometers. All right, so troopers, you see now that this prediction intervals and tolerance intervals are pretty easy. It's very much like what we have been doing already. Now this may or may not come up in your professional life, but again, you'll have a homework on prediction and tolerance intervals, and if you're worried about some of those earlier homeworks, you'll be able to go do that homework and hopefully replace some of those bad grades on lower numbered homeworks. Okay, well, that's pretty much it. Our final will be pretty much over chapters 7 and 8. Okay, so study up on those, and please stay safe, stay healthy, and when the fields are white with daisies, we'll meet again.